Hi everyone! In this video, we will finally benchmark the embedding models. We have collected everything. We have converted the text chunks and questions to dense vectors, and now all we need to do is to use few metrics to assess the performance of each model. You are going to compare the performance of the models in two different ways. First, we are going to do this manually. I will try to explain to you the metrics that we use to compare retrieval models or embedding models in this case. I'll show you the equations, I'll try to explain them to you, and after that we are going to move to a library called Ranx. This library will allow us to basically apply those metrics very quickly without writing a lot of code. And it also has something that is very interesting, which is statistical testing. And we really need this because sometimes we might get two models that perform very close to each other, but we don't have a way to say if they are similar or not. And by using statistical testing, we can get something that will tell us if those models are similar or not. Here is an example of what we will get in the end of this video. As you can see, we have the 7 models that I have used in the previous step. We have closed models and open source models. We are going to use both of them. And in the other columns, we have the metrics. We have 3 metrics, MRR, recall, and NDCG. And inside each column or inside each cell, we have the scores. And in the end, we'll see the best performing model and the worst performing model in this benchmark that I have created. And I will explain to you everything in this video. So don't worry about the letters that you see inside the cells. You will understand what they mean. You can also compare the models side by side to get a lot of information, like how many times a model wins against another, or how many times they tie, and how many times a model loses. And all this information we get thanks to Ranx. And here, for example, you can see that we are comparing the all-mini-LM model to, in this case, the smallest Qwen model. After that, against Gemini, the medium Qwen model, etc. And we will keep comparing the models pair by pair. And after that, for example, here you can see that all-mini-LM was able to win against the smallest Qwen embedding model 37 times, but it lost 111 times. So it means that the Qwen model is stronger than the all-mini-LM model. So this is something that you can also use in order to compare the models without looking at the scores. Here we have the p-value, which is very important, and we get this thanks to the statistical tests that Ranx performs for us. We will talk about this in the upcoming slides. Here I have used just 3 metrics, MRR, recall, and NDCG, but there are a lot of metrics that you can use. So I'll show you all of them and a list that will explain them to you and that will show you how to compute them. We are going to rely on statistical testing to analyze the difference in performance between 2 models. This is a really handy tool that we can use in order to basically say with confidence if a model is better than another or if they are close in performance. Here is the updated pipeline. In the previous step, we were here. We generated the dense vectors for the text chunks and the questions. And now in the evaluation step, we take those as input and output a ranking of the models. So for example, in our case, as you saw in the table, we have 7 models, and in the end, we will have a ranking that will rank those models. So yeah, this is what I'm seeing in these bullet points. The dense vectors are used in the evaluation step, and the output will be a rich comparison between the models. I will show you how to generate those 2 tables, and just by analyzing them, it will allow you to choose if you want to move to a new model or not. Now let's talk about the metrics. We use them in order to compare the performance of embedding models, and there are plenty of metrics that we can use. You have precision, R precision, recall, B-pref, F1, etc. So the list is big. I haven't showed you all the metrics, but if you are interested, you can click on this link in order to see all the metrics that you can use. You'll also find how to calculate them and how to use them in Ranx. In this course, I will use just these three: MRR, NDCG at K, and recall at K. And I will explain to you what at K means in the upcoming slide. Let's start with the mean reciprocal rank. This metric is used to measure how quickly the first relevant result appears in the ranked list. Let me show you the equation because it will explain to you how that works. Here is the equation. You can see that MRR is equal to 1 over rank. And in this case, rank is the position of the first relevant document. When I say first relevant document, I mean the correct document. If I take a question, I know that there is only one document or one text chunk that answers that question. And if that document appears at the first position, then rank is going to be equal to 1. And MRR is going to be equal to 1, which is the highest value. If that document appeared, let's say, at the 5th position, then MRR is going to be equal to 1 over 5, and the score is going to be very low. So this is what I mean by measures how quickly the first relevant result appears in the ranked list. Let's see an example to demonstrate this. Consider that you have 3 text chunks where one of them answers the question, and that chunk is marked by this star. Here I have 3 chunks and a question, and chunk 2 answers the question. The first step, so follow this pipeline with me. The first step you do is take all of these, give them to the embedding model, and as the output, you will get 4 dense vectors. Now we will take the question and calculate the distance or a similarity score between it and all the other text chunks. Here I chose to calculate the distance, but you can do the same thing if you want to use a similarity score. If you want to use distances, you can use, for example, the Euclidean distance or the Manhattan distance or the other distances. There are plenty of them. Or if you decide to use similarity functions, you can use, for example, the cosine similarity function, or you can use the dot product. You have plenty of similarity functions that you can use. So after calculating the distance between the question and the other text chunks, you will get 3 values. And here, if you decide to use distances, you will sort the chunks in an ascending order. Here, for example, 0.13 will be first, after that 0.23 and 0.69. But if you decide to use similarity functions, you will order the chunks in a descending order. Okay, so in that case, 0.69 will be first, then 0.23 and 0.13. But since I use distances, I ordered them in a ascending order. And as you can see, chunk 2 appeared last. So if I take the formula, and rank in this case is equal to 3 because the correct document appeared in the last position, and that gives me 1 over 3, which is equal to 0.33, which is low. A good embedding model should put this chunk in the first position, and in that case MRR will be equal to 1. Now let's move to recall at K. This metric indicates whether the correct document appears within the top K results. For datasets with one relevant document like ours, the equation is the following. So recall at K is equal to R divided by capital R. Small r is equal to 1 if the relevant document is in the top K results, otherwise it is set to 0. And capital R is equal to 1 because in our case we have one document that answers the question. But the formula that you see here is in the general case, and yeah, let's apply it to that same example. The recall score here is good because as we have seen, we have just one document that answers the question, so capital R is equal to 1. And here, because this document appeared in the top 3 results, small r is equal to 1. And 1 divided by 1 is equal to 1. Let's say that we have retrieved 3 documents, but chunk 2 was in the 4th position. In that case, small r is going to be equal to 0, and 0 divided by 1 is equal to 0. As you can see, recall is perfect, but the problem is that chunk 2 appears in the third position. So recall does not care if your document appears in the first position, second, or last. And this metric combines the previous two together into one metric that we call NDCG. And this one considers the position of the relevant document, unlike the recall at k. Let's see the equation. So the equation looks a bit complex, but let me explain it to you. First, we have two terms, DCG, which is discounted cumulative gain, and the ideal DCG. And ideal DCG means the best output that we can get from the embedding model, which means that the correct document should appear in the first position. If that's the case, then the ideal DCG will be equal to 1. But the formula that we will apply is this. So here we have two terms or two cases. If the document is within the top k results, we are going to apply this formula. Otherwise, it is considered equal to 0 because it doesn't appear in the top k results. And to get the NDCG, we take DCG and divide it by the ideal value. And because here in our case, the ideal DCG is equal to 1, NDCG is equal to DCG. This formula that I'm showing you here is valid for our case because we have just one document that answers the question. But if you want to apply this in the general case, make sure to click on that link that I showed you in the previous slide. It will show you the general formula. And like before, rank is the position of the correct document. Now let's apply this to the same example so that you understand how this works. So in our case, k is equal to 3 because we are retrieving just 3 documents. And let's look at chunk 2 because this one is the one that answers the question. Let's apply the formula. So the formula is 1 divided by log base 2, rank plus 1. Rank in this case is equal to 3, and this gives us 0.5. So as you can see, NDCG is smaller than recall and bigger than MRR. So with the mean reciprocal rank, we got 0.33. Recall gave us 1, and NDCG is between them. It gave us 0.5. Now let's move to the statistical test. And let me explain to you why we are going to use them. So this is the table that I showed you in the beginning. And here, after applying all those equations, all those metrics to every model, we get something that looks like this. Now, what does this mean? You can see that here, for example, if we look at this cell, we have 0.8075, but then we have these letters, A, C, F, G. This value means that the Qwen3 embedding 0.6 billion model is better than the models that have these letters. So A corresponds to all mini LM, C corresponds to Gemini, F to the text embedding small, and G corresponds to the large text embedding model from OpenAI. And if you look closely, in some cells we don't have these letters. That's because when we performed the statistical test, we realized that this model is not good than the other ones. And and we can see this. If we look at the all-mini LM, it has the smallest MRR score, the smallest recall score, and it's the worst model in this list. But if we look at the Qwen3 embedding 4 billion model, this one is the best model in this test that I performed. If you look at the scores in all metrics, you'll see that the Qwen3 embedding 4 billion has the highest scores. And if you look at the letters, it shows you that it's better than A, B, C, F, and G, but it's not better than the Qwen3 embedding 8 billion model because when we performed the tests, we saw that they are similar to each other because there isn't a big difference between these two models. And in order to get this insight, we need to perform those statistical tests. Ranx allows us to do that. And also, we get something interesting Here, you see that the performance of the quantity model is not due to chance because it is validated statistically. Because sometimes you might get lucky, or you can select the data in a way that you show that a model performs better than another. But if you enlarge the data set, you will not get lucky, and the model that is general will perform better than a poor model. And with statistical testing, we can prove that, and we can get this information very easily. And this is what I explain here. When you benchmark models, if you get a good score in a metric, that doesn't mean that this model is good. This model might have performed better than the other ones because it's got lucky, or because there is random noise in the data, or because you have selected the data in a way that shows that this model is better than the other ones. With statistical tests, we can determine if the performance difference between two models is real, which means that, yes, this model on paper is better than the other one. It's not due to chance or something else, or because you chose the data in a way that shows that this model is better. And these tests work by challenging something that we call the null hypothesis. We are going to dive a bit deeper in statistics, but the null hypothesis is something like this. Let's read it. So the null hypothesis in this case is the following. The two models are identical, and any difference in their mean scores is just due to random chance. Okay, so this is the null hypothesis. After that, we start running the tests. The output of the test is a probability that we call p-value. And this is the probability of seeing your results if the null hypothesis were true. And here is how it works. So basically, you set a threshold. Generally, we set it to 5%, but you can go lower if you want, or higher. You get the p-value. If this probability is smaller than 5%, we are going to reject the null hypothesis, and we are going to say with confidence that model A is better than model B, or model B is better than model A. But if the p-value is greater than the threshold, in this case, it's complicated. So we fail to reject the null hypothesis because we don't have enough evidence. So we are unsure if the model A is better than model B, or model B is better than model A. In this case, we don't have enough evidence, so we need to collect more data. And if this holds, then in the end, we say that the two models are basically similar in performance. With Ranx, we have access to 3 statistical tests: features randomization test, the students paired t-test, and Tukey's HST test. Don't worry about these. If you want, you can search for these tests online. You can learn more about them if you want, but it's very simple to use these tests within the Ranx library. And now let's try to benchmark two models. So let's say that model A was introduced, let's say in 2024, and this is our baseline. And we saw that a new model appeared in 2025. Let's call this the new model. We want to know if we should migrate to use model B. How do we do this? We are going to create a dataset, and we are going to benchmark the two models. We are going to test them on 5 queries using the NDCG metric. Here is a table that shows the score. So here we have the scores per model, and after that we calculate the mean scores. So here we can see that model B performed better than model A. But the question, is this difference significantly better, or did model B just got lucky in this test? Again, we are going to put the null hypothesis, and it says that there is no real difference between the two models. And the difference that we are seeing in the table is due to random choice, or random chance, sorry. So our goal is to see if we have enough evidence to reject this claim. Okay, let's start with the paired t-test. This one looks at the differences for each query. So let's do that. We have the two initial columns, and now we are going to add another column that will calculate the difference between the scores of these models. So here 0.6 minus 0.5 gives us 0.1, and we will apply the same operation to the other queries. Finally, we get a mean score that is equal to 0.06. The paired t-test checks if the mean of these differences is significantly different from 0. In the end, we get a p-value, and again, we compare it to a threshold. If it is smaller than the threshold, we reject the null hypothesis and we say with confidence that this new model that appeared in 2025 is better than the model that was introduced in 2024. In the other case, we reject that null hypothesis and we say that we don't have enough evidence, so we are unsure if this new model is better or not. Randomization test is a bit different. Let's see how it works. So this one, it simulates the random chance of the null hypothesis, because in the null hypothesis, we said that this difference is due to random chance. This test will try to simulate that. Let's see how that simulation is done. So initially we have a difference equal to 0.06. Now what we are going to do, we are going to shuffle the scores. So here, let's look at Q2 and Q4. So here initially model A scored 0.4 and model B scored 0.3. We are going to shuffle those. We are going to flip them. So model B will get the score from model A, and model A will get the score from model B. And we will do that for Q4. And then we will get another difference. And in this case, it's equal to 0.02. So this is the new difference. Now we are going to, or the test is going to apply this shuffling thousands of times to see the differences that we are going to get by chance. And in the end, we are going to count how many shuffles resulted in a difference of that initial value or more. So if we get, in this, let's consider that we got 850 out of 10,000. To get the p-value, we calculate those differences that are higher than the original one, and we divide that by the number of shuffles that we performed. Something that Ranx provides is the ability to see the wins, ties, and losses. And now, since you know a little bit about p-value, let's look at some examples. Let's look at the first row. We have all mini LM against the smallest quantity embedding model. Notice how p-value is equal to 0. And when a model is dominating, p-value is always very low. And how do you know that? Let's look at the losses and number of wins. So all mini LM was able to win 37 times. And here, winning means it got the highest score in certain questions. But Qrels was able to beat all mini LM in 111 questions, which is, the difference is very big. And they tied in 229 questions. So because Qrels is beating the all mini LM in a lot of questions, it's dominating. So the test confirms that, and it gave us a small p-value. In Ranx, you can set the threshold. And if we compare this to 5%, it's low, so we reject the null hypothesis. But in other cases, you can see that here the p-value is very large. When you see this, it means that the models are similar in performance. Let's take the Qwen models, because I talked about them in when I was explaining the values inside the cells. And I mentioned that the 4 billion and 8 billion versions are similar in performance. So let's look at this example. Or let's look at the second one because it has the highest p-value. So in recall at 1, both models tied in 352 questions. Qwen, the 4 billion, was able to win in 14 questions, and it lost in 11 questions. So you can see that there isn't a big difference between the number of wins and losses. This is why the p-value is high. But let's look at this one. So here you have 9 and here you have 2. In this case, recall at 5, the 4 billion model performed better, and the p-value is not lower than the threshold. But yeah, if you look at all of them, you see that both models are similar in performance. So that is it. I hope that you enjoyed this part. I know that there is a lot of information in this step, but I tried to show you everything so that you understand what we are going to do in the notebook. And you will see that the notebook is very simple. You will understand everything if you have followed the first part of this video. So now let's stop talking about theory and let's start coding. Before I show you the notebook, if you haven't cloned the repository, make sure to do that and try to run the notebook alongside me so that you can understand things, because just watching a course will not benefit you much. You will find the link to the repository in the video description. Open the code base inside your preferred IDE and open these two notebooks, 5.1 and 5.2. I mentioned in the slides that I will show you how to do this manually, and then we will move to Ranx. The dataset that I am using here is the one that we generated in the previous video, and I have mentioned because the size of this dataset is big, I was not able to push it to GitHub, but I will put it in Hugging Face and maybe Kaggle too, and so that you can download it. So after you download this, make sure to put it inside the embeddings folder. Let me show you. If I scroll up, I have the data folder. Inside it, I have the embeddings folder, and here is the file that we are working with. So let me load it and let's look at the statistics. So we have 43 text chunks and 377 questions. The first thing that we are going to do is talk about the evaluation metrics. We have 3: MRR, recall, and NDCG. If you want to read more about the metrics, click on this link. It's the same link that I showed you in the slides. And as you can see, we have a lot of metrics and you can click on all of them. Let me show you. I can click on DCG and here is the general formula if you want to apply it. So let's start with the mean reciprocal rank. Here is the formula. It's 1/rank, and here is how to do that in Python. If for some reason rank is not defined, we are going to return 0. Otherwise, we are going to write the formula. So this one is simple. Now let's move to recall at k. The general formula looks like this, but since we have just one document that answers the question, we can simplify it by setting capital R to 1. And this gives us something very simple. So recall at k is going to be equal to R. We return 1 if rank is within the top k results, otherwise it's 0. Finally, we move to the NDCG metric. It looks a bit scary, but we are going to simplify it because in our dataset, we have just one document that answers the question. So NDCG at k becomes DCG at k, and here is the formula. If the rank is within the top k results, we write this formula. Here it is, 1 divided by log 2 rank plus 1. Otherwise, if the document is outside the top k results, we return 0. Great. So now let me define all these methods. And now let's continue. So first of all, let's get the list of embedding models. I'm going to get them from one of the chunks that I have in the dataset. And as you can see, we have 7 models. Now we are going to create a mapping from each question to its correct chunk. This is why we created that chunk ID in the beginning, so that we can link the question, the question to the answer. And the answer to that question is the chunk. The first 4 questions can be answered by the first text chunk. And here how many? 1, 2, 3, 4, 5, 6, 7, 8. And the next 8 questions can be answered by the first chunk. So here we are just linking each question to the document that answers it. Let's continue. And here we just extract the IDs from the chunks list. They are going to be in order. And now in this cell, we are going to create NumPy arrays because we are going to calculate similarity between the dense vectors. And by converting them to NumPy arrays, we can make these calculations efficiently. So let me show you how that looks like. So I can take the chunk embeddings, let me put it here. And after that, let's look at it. So this is a dictionary where we store the dense vectors per model. So now let me take, for example, this model, and let me look at what we have inside. So let's do this. And this is the result. And this is an array. Let's look at the shape. We have 43 text chunks, and each vector contains 1024 values. So this is the dimension of the embedding vector. And we can do the same thing for the questions. We saw that we have 377 questions, and this is what we get. Great, so let's keep going. So I've done this for Gemini also, and Gemini has 3072 values per dense vector, and the 8 billion Qwen tree model can go up to 4000 values. Now let's run the manual benchmark. Here I'm explaining how the loop works. First of all, for each model, we calculate the cosine similarity. As I mentioned in the slides, you can either use similarity functions or calculate distances. So here I went with using similarity scores, and I'm going to use the cosine similarity method. And we are going to do this between every question and all chunks. And after that, for each question, we are going to rank those chunks by similarity and find the position of the correct chunk. After that, we compute the 4 metrics like how I showed you in the slides for each question, and then we are going to average the scores for each metric. Let's see this in action in code. So here we start by defining this method that I called getRank, and it's going to give us the rank of the correct chunk. So here we have the list of the rank chunk IDs, and we have the ID for the correct chunk. We get the index and we add 1, so that we start from 1. If for some reason we don't find it, we are going to return none. Okay, but let's start. So for every model, we are going to get the question embeddings, the chunk embeddings, and we are going to use the cosine similarity function from scikit-learn. And because it accepts NumPy arrays, it's simple. So it's going to perform that calculation over these two matrices, and it's going to give us a similarity matrix. So inside this similarity matrix, we have the similarity score between the questions and the corresponding text chunks. Let me show you how this works. So I can take this, put it here. Let me define GQDM also, and the cosine similarity. I will also add a break. I always like to do this because you need to try to understand each iteration individually before running the full for loop. And yeah, let's just run this. So it ran, everything worked. And now let's start looking at the shapes. So if I take all question embeddings for that specific model, we get the same thing. And here we start with the all mini LM. I know that's because the shape or the dimension of the dense vector is small. And we can look also at the chunks. It should be, let's not look at the similarity matrix for now, but the chunk embedding should be 43 because we have 43 text chunks. Now we have also the similarity matrix. Let's look at it. So it's going to be 377 by 43. And this calculates the similarity score between every chunk and question. So we have everything here. And let me show you this. So we can print it. You can see that the values are going to be between -1 and 1 because we are using the cosine similarity matrix. And now we loop over the questions. Let me take this whole block and put it here. Okay, and let's add a break. Okay, so we get rank, and here let's try to print all of these. So let's take this, let's delete everything, and let's replace that by print. We need to define the getRank method, so let's put it here. We have our break statement. Let's run this. Okay, so we were able to calculate the metrics, but how did that work? So first of all, we get one question. We need to know the document that answers it. So we need to use the ground truth mapping. And let's look at ground truth. So ground truth is this dictionary that we created to map from each question to its correct chunk. For example, if I am looking at the first question, the ID of the first chunk is 0. So this is what I am getting here. And let's verify that. If I look at the correct chunk ID, it's equal to 0 because I am looking at the first question. Let's keep going. And after that, I'm going to get the similarity matrix and look at the same index. So let's look at that. So scores for this question. Here, if I look at the shape, we will have 43. Why? Because we have 43 text chunks. So this is the similarity score between that question and the other documents. If you remember the pipeline, let me show you the pipeline. Here it is. So we were able to compute these similarity scores. Here they are, all of them. Now we need to sort. Let's see. As you can see, we are going to sort them. Let's look at the sorted scores. Let's put them here. And yeah, as you can see, the scores are sorted. So the first one has 0.27, 26, 23, etc. And after that, you get the chunk ID alongside that, the score. Now let's look at chunk scores. And here we are using this list that contains the IDs for the chunks, and we are zipping it with the scores. Let's see what this does. So chunk scores is going to be like this. So as you can see, each document or each text chunk has its own similarity score with the question. And now we use the sorted method to sort that. We want to sort it by the score, not by the chunk ID. That's why we are selecting the second item in that tuple. After that, we get the chunk IDs. Let's look at them. Here they are. And we use the getRank method to give us the rank of the correct document. And we know that the correct document is 0. Here it is. It's 0. And if we count 1, 2, 3, 4, 5, 12. So this gives us 12. Let's look at rank and let's validate this. Yes, so it gives us 12. And now we apply the formulas. So MRR is 1 divided by rank. Let's validate that. So I can take 1 divided by rank. It gave us 0.08. Since the rank is very big, it's 12, it's not appearing in the top K result. That's why we got 0, 0, and 0. So yeah, it's working. And now I can remove these because I explained to you how those work. And I can also remove this. Now let's go back. Now we're on this in a loop. So we are here. And in the end, once we append all these results, we are going to calculate the mean. Because we have how many questions here? We have 377 questions. And in the end, we just want to get one score. That's why we calculate the mean for each metric and put that in a dictionary. Let's run this. It's finished. And yeah, we can look at these scores. So here we have the metrics. We can calculate the max and the minimum score for all of them and print them here. So the maximum, let's see. So the maximum MRR is 0.83 and the minimum MRR is 0.71. We are calculating this so that we can highlight the worst and best model. And here we are using the rich library to be able to generate a table that looks nice in the output of the notebook. I have also created this cell that will create another column that will average the metrics and then sort the models based on the average. We can clearly see that the All-Mini LM is the worst model and the medium and large Qwen tree embedding models are the best. You can see that here we don't have those comparisons because we are doing this manually, and here I am not doing the statistical testing. I want to show you this in the second notebook. Now we can close this notebook and go to the second one. We do the same thing. First, we load the dataset. We have the correct number of chunks and questions. And after that, we start working with the Ranx library. Here we start with something they call query relevance judgments. This is the same mapping that we have done before. Let me run this cell because it takes a few seconds to complete. So it took 2 seconds. So we give this method the questions, and here we create a dictionary. Basically, this will map the question. So here we have the query ID. Let's look at it. So let me show you. this is how you should try to run these notebooks. Try to take something from within a method and try to run it manually. And this is why in my courses, I try to create notebooks instead of Python scripts, because with notebooks, you can dive deeper and try to understand everything by running them in cells. If I take this, let me show you this dictionary. And this is the mapping. This is exactly what we have done before. You can see that the first 4 questions, here we have the first 4 questions, and we gave them 1. And here, for example, the second, I think here we have 8 questions. They all map to the second chunk, etc. So this is the content of Qrels dictionary, and you can click here if you want to read more about this class. Here it is, and they show you how to instantiate that. And here, let me zoom in. Here they are showing an example where 2 documents can answer a question. In our case, we have just 1 question, but this is the general case. You can have more than 1 document that answers a single question. And you can see that sometimes that document can answer 2 questions. For example, the second document appears in the first question and in the second question. Now let's go back to the notebook. We created the Qrels. Now we create the runs. Again, click here because that will take you to the documentation. And here they show you how to create a run. And here you can read more about this. And here is how we do this. And we are going to have multiple runs, 1 per model. Let's run this, and as you can see, here we have the models to benchmark. This is a list that contains the model names. Here they are. And now for each model, we are going to create a run. And that run will take chunks, questions, and model name. Okay, now let's go inside the create run from data, and let's look at it. So first of all, we create an empty dictionary. We retrieve the chunk and question embeddings from that model. So here we have our chunks and questions. We calculate the similarity scores. We get the chunk IDs from the chunks list. And now we are going to loop over the similarity scores. And for each chunk ID, we are going to put the score related to it. So here inside chunk scores, we are going to have, for example, the first chunk will have a score, the second chunk will have another score, etc. And we put that inside this run dictionary, and it should have the same query key that we used here when we created the Qrels. You can see that the Qrels, this is the key. It has this prefix Q underscore, and we are using the same thing. But here we are putting the chunk scores. I know that it's very hard to understand this just by reading the code, but again, we will do the same thing. We are going to copy the code. Let's put it here, but we need a model name. So let's take the first one from this list. Or actually, let's see. Let's take 0, 1, 2, 3, 4. Let's take this one. And let's go through this step by step. So let's take the first part. Here we have the chunk embeddings. Let's look at the shape, chunk embeddings dot shape, and question embeddings and similarity scores. Okay, so we have 43 text chunks. The size of the embedding vector is 4096 because we are using one of the big embedding models. Yeah, we are using the 8 billion quantity model. We have 377 questions, and the similarity score is correct. Great. Now let's continue and let's look at this. And here, since we have a for loop, let's add a break statement and let's look at this. We are interested in chunk scores. Okay, so let's run this, take chunk scores, and let's look at this. You can see that here we have a mapping between the chunk ID and the scores. So here the first chunk has this score, 51, the second one, 0.44, etc. So this is the content of chunk stores, and the run dictionary will be like this. So you have that specific prefix Q underscore, and because this is the first question, yeah, because here when we use enumerate, it's going to loop, let me show you the shape. It's going to loop over the questions, not the text chunks. So this loop will run from 0 up to 376. Let me remove the break and show you that. So if I print the keys, you will see that the last value is 376. And this is the format that Ranx expects you to use when creating the Qrels and runs. And based on these two, Ranx will try to calculate the metrics and perform the statistical testing. So far there is no calculation. We are just preparing the data for Ranx. We have the Qrels and we have the runs. Now here's how it works. You can see that we use this compare method. We give it the Qrels and runs and the metrics that we want to take into consideration. So we have MRR, recall at 1, recall at 5, NDCG at 5, and I could add more if I wanted to. If you want to go back to the documentation, click here, go down until you find metrics, and here you can just take these values. So if you want to add hits, take the alias and put it there. If you want to add F1, take it from here and add it to this list. If you don't know which metric supports the @k notation, you can come here and look at the @k column. If you see yes, that means that you can take the alias and add a number like we did here. So if I go to recall, you can see that we have yes, so which means that I can type recall at k. And after that, you set the maximum threshold. Here it's set to 5%. And the statistical test. Here I set it to Fisher, but if you hover over this and scroll a little bit down, you'll see that you can set other statistical tests. Use Fisher if you want to use the Fisher's randomization test. Set it to student if you want to use the paired student t-test. And finally, you have Tukey for the Tukey HACD test. If I run this, it took 1.4 seconds and it performed the same thing that we performed in the other notebook, meaning it calculated the metrics and on top of that, it performed this statistical test. So let's display the results. But first we need to assign each model a letter. So OmniLM will get A, etc. And now we can print this. Up to this point, I'm just trying to make the tables look nice. Here we are calculating the maximum and minimum scores. And finally, we reach this cell where we print the data. And I think I also have, I have done the same thing. So I calculate the average and rank the models accordingly. As you can see, we have those letters that I showed you in the slides. And it makes sense that we don't have letters here because this is the worst model and all of them are better than the A model. And here the 4 billion model is better than all of them. Same thing with the 8 billion model. Let's try to analyze what we have here in the cells. You can see that I mentioned that NDCG is a combination of MRR and recall. Let's see why. So MRR for the Qwen model is 0.83, recall is 0.96, but NDCG is 0.86. So it falls in between MRR and recall at 5. Because here recall doesn't care about the position of the document, but NDCG does. So in order to print the win, tie, and loss table, we have this win, tie, loss dictionary from that report. Yeah, let's look at it here. So we have the report and we have the win, tie, loss attribute, and it contains everything. Here it's compared the all-mini-LM with the small Qwen model, and it gives you the wins, ties, and losses per metric. And here we can see that wins and losses are shown for the first model. So this means that all-mini-LM won 37 times and it lost 111 times, etc. You get the same thing for recall and NDCG. So I basically took what I have here in order to generate the second table, which I create here in this cell. The table is big because here we compare all the models against each other. Here, all-mini-LM loses every single time because it's the worst model. But with the 4 billion and 8 billion model, they are similar to each other, but still the 4 billion beats the 8 billion model. And how do we know this? We just look at the p-value. Here, if we go back to the all-mini-LM, the performance of this model is poor. That's why the p-value is small, because this model is way better than the all-mini-LM. But once we go a bit down and look at the 4 billion model and 8 billion model, we saw that the scores are close to each other. This is why the p-value is larger than the 5% that we set as a threshold. Just by looking at this, we can't reject the null hypothesis. And this is why, if I go back to the first table, we saw that we don't have a we don't have an E letter here with 4 billion, because it means that the test that we performed showed that the 4 billion model is not better significantly than the 8 billion model. They are both performing well, and we can use either one of them. So if, for example, the 4 billion is cheaper than the 8 billion, it's better to use the 4 billion model. But at this stage, we cannot conclude. Why? Because here I am just using one document. I am planning in the upcoming videos to show you how these models are going to evolve once I keep increasing the size of the dataset and keep adding documents from different domains. Behind the scenes, I'll try to increase the number of documents, and we'll see if the 8 billion model will hold or the 4 billion model. And what I like about doing this manually is that we validate the performance of the models. If you remember, I've shared with you the MTab leaderboard 2 times in the slides. And here, if we look at this leaderboard, we can see that the Qwen 8 billion model is better than the 4 billion model. And Gemini embedding sets in between. We got something similar, but in our case, the 4 billion was better than the 8 billion model. This is a big data set. It contains a lot of tasks. That's why here the 8 billion model was able to generalize a lot, and it's got a better mean score. So if we come here, the mean score here is 70%, and with the 4 billion model is 69%. You can see that even here in the MTab leaderboard, the performance of these models is almost similar. But here in this case, the 8 billion model was able to beat the 4 billion. If we look back, we see that the 0.6 billion model appears after the 4 billion and the 8 billion models. We need to make the datasets big because sometimes you might have models that are good in English, and other models might be good just in French. Some models are going to work very well on multiple languages. We will see these things in the upcoming videos. We are going to translate the dataset. We are going to add more documents, and these scores are going to converge into one stable configuration in the end. This is the last thing that we do in this notebook, and I went very quickly through these cells that create the tables, because here we are just displaying the data. There is nothing very important here. What's important is what I showed you in the beginning of the notebook, where we talked about the metrics and the statistical tests. Here, increase this to 10 and do the same thing here. I can quickly generate another table and look at the data. So let's do that quickly. And yeah, as you can see, we have another table and the metrics have changed. Now we have recall at 10. Look at the recall. Now we are getting almost perfect scores, because when you increase the recall, the task becomes very simple for the embedded models. So the best thing to do is to keep the recall small, because here, recall at 1, the scores are low. But if you increase the recall, then this becomes very easy. And the recall and the value of k depends on the size of your dataset. If you are working with hundreds of thousands of documents or text chunks, in that case, you can set k to something around 100 or 200. But if you are working with 1,000 or 2,000 documents, setting it to 100 will make it very easy for the embedded models. But yeah, I'm just showing you here that you can change this easily if you want to. So that is it for this video. In the next one, I will try to work hard by generating more data. And after adding more documents, after creating more questions, I will show you the progression. So currently I have almost 400 questions. My plan is to generate another 400, do the benchmark, and then generate another 400 questions, do the benchmark, and after generating maybe 1200 questions, I'll come back to you with another video where we show the progression. So I will show you how the scores were in when we had just 400 questions, then how they changed when we had 800 questions, and finally when the dataset is big enough where we will have maybe 1200 questions or more. When we reach that, we will have a large dataset that will give us a real idea of how these models perform. And until then, have a wonderful day. See you in the next video.